Hello, welcome back to A Slice of Physics. We have recently been talking about magnetic fields from wires that are long and straight that carry a current, and now we're ready to discuss some other configurations. In this video, we'll talk about magnetic field from a current loop, and in the next one, we'll talk about a solenoid. So our goal in this video is to understand the magnitude and direction of magnetic field from a current loop. So let's get started. I'm going to take a current in a loop. So in this case, the wire is in this arrangement, and presumably it continues like that and like this over here. So you could have a current going through it, but we're interested in just the loop part, not the extensions of it. So let's say the current goes in here and it travels this way along the loop and exits the loop to the right. And we want to understand the magnetic field from this current loop. We're going to talk about direction everywhere inside the loop. We're only interested in inside more so than outside. And then in particular, we'll talk about the magnitude of the magnetic field at the very center. It is not uniform. You know that magnetic field is stronger near the wire and weaker farther away. And then this loop has wires all around it. So there will be magnetic field strengths that are varying inside the loop, but we will talk about the equation for the magnitude at the very center. The way we represent this for analysis, it's easier if I can flip this loop and rotate it in three-dimensional space. So let's say there's an axis over here and I spin this entire loop this way. So I'm pushing this end into the page and pulling this end out of the page, okay? So if I do that by 90 degrees, the loop then ends up looking like this. So when I turn it by 90 degrees, I will only see the cross section of it. So I will see the curved things at the bottom and the top, and I'll just see a straight line here representing the front side and the back side. So this will be our front side, this will be our back side. So in this case, as I pull this left end out and push the right end in, the current at the very top is going to be going into the page. I hope you see that. So I'll show that as an X here, because as I pull this out, the left end of this wire is going to be outside the screen, between you and the screen. So the current is going in, and then it'll be coming out of the screen at the bottom. So we show that as a dot. And if I were to show the current in the front end of this, the current in the near end is going to be going up like that. And in the far end that's inside the page, the current will be going down. So I'll show that as a dotted arrow. Hopefully you see that representation. The current's going up in the loop cross section here, into the page at the top, down behind the screen, and out of the screen at the bottom. Okay, so that's how we represent it, because it becomes easier for us to talk about the direction of the magnetic field. All right, the way we want to analyze this is by taking small segments of this circular wire and pretending that they are straight. So let me take 4 small segments. I'm going to take the first one is going to be this guy at the very top. Let me number them. The second one will be this guy at the very bottom. The near end of the coil is going to be 3, and the far end of the coil behind the screen is going to be 4. So let's do that. Let's take the small short segment that's going into the page at the very top and see what happens. So if I take that short segment, short straight segment, we know how to deal with this. We use our first right hand rule, and we orient our right hand as a thumbs up. We rotate it to place the thumb right here at this wire with the thumb pointing into the page. And you will see when you do that, that the rest of your fingers curl this way. So the direction of the magnetic field from this short segment at the very top is going to be like that. Okay. I'm going to offset all of these different segments and then we'll put it together. Now, looking at the second one, at the very bottom, I've got the current coming out of the page. So now I place my right hand as a thumbs up sign. I put my hand over on top of this wire at the bottom on this green wire and have my thumb pointing out of the screen. And when I do that, my fingers are curling this way. That gives us a sense of direction of magnetic field from the bottom segment, like that. The third segment, let's take the one that's near us, which means that's this straight end that's going up. Number 3, that's between us and the screen. So it's a short segment that is over here that we're considering at the near end. Sorry, let me change colors. And this near segment is a straight wire that looks like this, and the current is going up through it. And so now I can use my right hand rule, and the thumb will be pointing like this. The fingers will be curling this way. So I'm just showing one finger. This is my thumb, and the fingers are curling that way. So they would be, the magnetic field would be going like this. And lastly, to complete this, if I take the back end of this segment, which is behind the screen, so this will be the back end or the far end, it'll be this little portion segment over here, and the current in that segment is going down. So now I again use my right hand, make a thumbs up sign, and then I flip it 180 degrees. So this is more like a thumbs down sign with the thumb lined up against this wire. So my thumb is pointing this way and my fingers are curling like so, behind the wire there and coming back in the front over here. So my magnetic field direction would be that. All right, let's see what happens when we put all this together in the loop that's here at the top. So as we have seen from this very top one, which is over here, with the current going into the page, the magnetic field is clockwise. So I will show that like this. The magnetic field from the second segment at the bottom is counterclockwise for the current coming out. So that looks like that. And the current from this near segment 3 will be going like that and then coming out. This is a third dimensional thing that I'm showing. Hopefully you see what I'm implying here. It's going right to left at the center of the coil and then left to right in front of the coil. And then the number 4 will do the same thing, but let's not show that because it gets a little too crowded here. But the sense of magnetic field that you see here is like this. So if I put all this together and draw more magnetic field lines, you see that the magnetic field of a current carrying loop is going to look like this. So in this case, it'll be going right to left at the center of the coil. And lastly, we have an equation for what the magnitude of that magnetic field is, and it's going to be B is equal to mu naught I over 2R when there is a single coil. So mu naught is the constant that we've already been working with. I is the current in this loop, and R is the radius of the loop. And this equation only gives us the magnitude of magnetic field at one very special point. And that point is at the very center of this loop. So this very center here, and here it'll be this center. And the direction we have figured out using the right-hand rule in all these segments is that it's going to be going to the left. The magnitude of that magnetic field at the very center is given by this equation. So it depends only on the current in the coil and the radius of the coil itself. Now, sometimes in our applications, we will have a current loop which has multiple coils where the wire is wrapped on top of itself. So this is still a flat coil. It does not have no length in this direction. But I can have multiple loops of the wire coiled on top of itself. And when you have very thin wires, it's easy to do that. So when we do that, this equation changes to a little bit more of a general form. So instead of just the I in the numerator, it's going to be mu naught Ni over 2R. So this is our general equation for magnetic field from a current carrying coil. And of course, this N here is going to be the number of loops or number of turns of the wire. So to recap, we talked about the magnetic field from a current loop in this video. At first, we discussed that the current loop is a circular wire carrying a current, and we can have multiple loops that are wrapped tightly into a flat coil. The coil has no length, so to speak. And the way we analyze this for direction of the magnetic field is to take that circular coil into short, straight segments, and then we use the right-hand rule to determine the direction of the magnetic field, which told us which way it was going at the very center of the coil. And then we have an equation, B equals mu naught Ni over 2R, that gives us the magnitude of the magnetic field only at the very center of the coil. Thank you.